Hey guys, welcome to video 46. We're going to continue our discussion of small signal common source amplifiers by doing the derivation of the voltage gain for the unbypassed common source amplifier. All right, in the last video, the end result was given, that is voltage gain is negative GM times R prime D over 1 plus GM times R prime S. And now we're going to see where this comes from. So let's go on over to the next page and look at the small signal model for the MOSFET in this circuit. All right, the first thing I'm going to do is Kirchhoff's voltage law around this left-hand loop, which gives me 0 equals Vin minus VGS minus the drop across R prime S, which is I sub D times R prime S. And we know that the drain current is equal to GM times VGS. So now we're going to substitute this into the first equation, which gives us 0 equals Vin minus VGS minus GM times VGS times R prime S. And I'm going to solve this equation for VGS now. We'll see why in a couple minutes, but if I subtract Vn from both sides and then multiply by -1, it'll clear these negative signs, and we're going to get Vn equals VGS plus GM times VGS times R prime S. Now I'm going to factor VGS out of both of these terms, and that gives me VGS times 1 plus GM times R prime S. All right, and now I'm solving for VGS, so I'll just divide both sides by the factor in parentheses, which gives me VGS equals Vn divided by 1 plus GM times R prime S. Now the next thing I want to do is take a look at this right-hand side of the circuit, and V out, we know, is given by negative ID times R prime D. And what I want to do is define I sub D in terms of VGS and Vn from this equation over here. So we know ID equals GM times VGS, so V out equals negative GM times VGS times R prime D. And now I can substitute this identity for VGS into this equation, which gives me V out equals negative GM times Vn times R prime D divided by 1 plus GM times R prime S. All right, and if I divide both sides by Vn, I get voltage gain, that is AV equals V out over Vn, which equals negative GM times R prime D divided by 1 plus GM times R prime S. And there we go. There's our equation for the voltage gain of the unbypassed common source amplifier. Now I do have a nice version of this derivation here, and if you look through it, there may be a few slight differences between this and the previous derivation I just did, but every time I analyze a complex circuit like this, I probably do things a little bit differently each time, but in the end it's all self-consistent and we do get the same result. Now let's go over and look at the amplifier we analyzed in the previous video. Here it is, except now I've removed the source bypass capacitor. All of the previous measurements are shown here, and since I have removed the bypass cap, now our voltage gain is going to be significantly lower. If we go through the numbers, we come out here with a gain of negative 2.4. Now looking at the scope trace over here, I built the amplifier and I applied an input of 1 volt peak to peak. The output was 2.32 volts peak to peak, so our gain was negative 2.32, which is really close to the predicted value. And that's to be expected. We've got a lot of negative feedback because of the presence of RS, and negative feedback makes the voltage gain very linear and very predictable, and that's what we've got here. Now I also calculated the large signal limits. We've got VO max, the positive clipping level. That should be 2.3 volts. And if we look over here, we see it's about 3 volts, which is even better. VO min is the negative clipping level. That works out to be about minus 4.7 volts. The measured value is about minus 4, so it's not quite as good, but it's still a reasonable estimate. And if you need to brush up on the large signal analysis stuff, AC load lines and so on, go back to video 31 and you can get a good review of that material. Now what I want to do next is take a deep dive into the analysis of the drain feedback biased common source amplifier. On the left side of the screen we have the actual circuit, and beside it here we've got the DC equivalent. All the coupling capacitors have been replaced by open circuits. And we also have the analysis equations if you want to determine a drain current using the quadratic formula. We covered that previously, so I won't go through that here. Now, what I want to do at this point is look at the AC equivalent circuit and the small signal model. We're going to begin with the derivation of the input resistance for this amplifier, and I'm not going to lie to you, this is a tough one. For such a small circuit, it really generates a lot of work, but I think it's kind of interesting, so please bear with me and we'll try and get through this, okay? So what I'm going to do first is KVL around this outside loop of the small signal model, and that gives me 0 equals V in minus the drop across RF, and that would be I sub F times RF, minus V out. And since we know V out equals negative ID times RD, that would be V in minus IF times RF minus negative ID times V R prime D. So we're going to make that plus I sub D times R prime D. All right, now we have one equation with two unknowns. I sub F is unknown and I sub D is unknown. So we have to fix that problem. And what we're going to do is Kirchhoff's current law here at node D. I'm going to define these currents, and let's start with this. We know that GM times V in, this current is equal to I sub F plus I sub D. All right, and what I'm going to do then is solve this for I sub D and substitute back into this equation to get rid of one of the unknowns. Okay, so if we solve this for I sub D is equal to GM times V in minus I sub F, and we can substitute this into this term right here. Okay, let's go ahead and do that. So we've got 0 equals V in minus I sub F times RF plus I sub D, which is GM V in minus IF times R prime D. Now we're going to distribute R prime D through here, and let me hope I can make this a little neater. V in minus I sub F R sub F plus GM times V in times R prime D minus I sub F times R prime D. Now let's solve this equation for I sub F. Let's move all the terms that don't have I sub F over to the left-hand side. So that gives us negative V in minus GM times V in times R prime D equals negative I sub F times RF minus I sub F times R prime D. And let's get rid of all these negative signs. We'll multiply both sides by -1. So that gives us V in plus GM times V in times R prime D equals I sub F times RF plus I sub F times R prime D. And we're almost there. We're going to factor I sub F out of these two terms. So that gives us I sub F times RF plus R prime D. And finally, we divide both sides by the term or factor in parentheses, and we get I sub f equals Vn plus Gm times Vn times R prime D divided by Rf plus R prime D. All right, now let's do one more thing with this equation. I want to make it a little nicer to work with. I'm going to factor Vn out of the numerator and put it outside of the fraction. Okay, so that's going to give me, let me come up here with this. That gives me I sub f equals Vn times 1 plus Gm times R prime D over R sub f plus R prime D. All right, now I hope you're hanging with me. This is a tough one, I know that, and if you find this cryptic, I sympathize with you, but we're almost there. All right, what we're going to do next is jump back over to our circuit and think about this for a second. The input resistance is equal to Vn divided by In, okay? And, well, In also happens to be I sub f, so we can write Vn over I sub f, and we have the equation for I sub f over here. So, Rn is equal to Vn divided by this whole mess, and that would give us Vn over all of this. This cancels, we get 1, and since we're dividing by this, we'll just multiply by the reciprocal, and we've got Rn equals Rf plus R prime D over 1 plus Gm times R prime D. And there's our input resistance equation. We finally made it. All right, now that was tough, and I don't know what to tell you. You just eventually get good at this kind of stuff, or maybe not. It does take a lot of work and kind of some insights into circuits that takes a while to develop. But it's like doing push-ups and pull-ups. It's tough, but the more you do it, the better you get at it, and it's good for you. So hopefully, you know, this is a good learning experience for you. But there's our input resistance equation for this circuit. We can make a slight simplification to this equation, though, by noting that generally RF is going to be very, very large compared to R prime D. So it's not going to have much effect. We can eliminate R prime D from the numerator without having any major effects. So we could also say that Rn is approximately equal to R sub f divided by 1 plus Gm times R prime D. And you could think of this as the voltage gain plus 1, Rf over 1 plus A sub V, Rf over 1 plus A sub V. And you'll see this in other places, in particular something called Miller's theorem that we use to analyze resistances and capacitances in the feedback loop of an amplifier. And you'll see this in that application. But for right now, let's just stick with our circuit oriented equation here, okay? And this is the approximation that is very often used in all the textbooks. And note that the input resistance is lower than RF because this denominator can be, you know, 10, 20, 30 or more. So RF generally has to be large to keep our input resistance large. All right, now you guys know I'm not going to leave you with my messy writing here. I'm going to give you a nice version of this derivation, and here it is. Now there may be some differences in the minor details along the steps, because every time I do a complicated derivation or problem, I do it differently. But thankfully, all the circuit analysis laws are consistent, and we always end up at the same place in the end. So here you go. And what we're going to do next is derive the voltage gain equation for this circuit. All right, let's go to the next slide. And here you see the derivation of the voltage gain for this amplifier. Rather than me going through it by hand this time, I figured I would just give you the nice version right from the beginning. The equation numbers refer back to my previous derivation on the other page, but when we crunch through all the algebra and we finally end up with an answer, we have the voltage gain equals negative GM times R prime D. That's the usual voltage gain equation for a common source amplifier with no source resistance. And we're adding this other term here that reduces the gain magnitude. Remember, this is a negative gain, and we're adding the gain times this factor over here. Now, fortunately for us, RF is usually very, very large compared to R prime D, so this fraction is going to be a small number, and the error term that we're adding to our normal voltage gain is not very much, so we can approximate the gain as negative GM times R prime D. But if for some reason you have a low value of RF, then you might have to go back and use this equation. And there may be times when it would be advantageous for us to have it in this form, but most of the time this is what you're going to see. All right, let's apply this newly acquired information in the analysis of an actual amplifier. Here we've got the drain feedback biased common source amp running from a 9-volt battery, and I've already determined I sub D using the quadratic formula here. The constants are A is 225,000, B equals negative 2251, and C equals 5.625. Plugging these into the quadratic formula, we get a drain current of 4.9 milliamps, and determining VGS, we end up with 1.72 volts. All right, now we could also do this graphically, and I'll call up Desmos here, and I've already got my transconductance equation for the parabola here. So what we're going to enter into the second line is our power supply voltage 9 volts minus X, which represents VGS. And in the denominator, we enter our drain resistor 1500 ohms. And there's our line, and here is our drain current, 4.853, about 4.9 milliamps, and 1.72 volts for VGS. 4.9 milliamps, 1.72 volts, so everything looks good. Our VDS equals VGS for this circuit, so we've got 1.72 volts, and that's because there's no current flow through RF, so the voltage drop from drain to gate is 0 volts. VDS equals VGS. Transconductance works out to be 44 millimos. And using the long accurate voltage gain equation, we get negative 33 plus 0.026, which is about negative 33. Again, this error term is very small because RF is very large compared to R prime D. All right, the last amplifier parameter we have here is the input resistance, and that works out to be about 29.4 k ohms, which is a lot lower than you might suspect looking at the circuit, but because RF is in the feedback loop of an inverting amplifier, it's going to appear smaller from the perspective of the input voltage. And one last thing before we move on, for this circuit, remember, because VDS is equal to VGS, which is a small voltage, we're not going to have much headroom for voltage output swing in the negative direction. So we have to restrict our output voltage to a relatively low value to keep this amplifier from distorting. All right, and we're going to see that in a second, because now we're going to look at the experimental evaluation of this circuit. All right. I built the circuit, and I thought I'd add a little color to the video here by showing a picture of my setup. Here's the actual circuit, and let's compare the theoretical values to the measured values here. Starting with IDQ, we calculated 4.9 milliamps. I got 4.8 milliamps from my experimental circuit, which is good. VGSQ was 1.75, which is also in good agreement. VDSQ, of course, is the same. And the one thing that's off the most is the voltage gain. I measured a gain of negative 19.4. versus negative 33 in our calculations, and that's pretty typical. Again, most of the time when you actually build these kinds of circuits, the gain is lower than the theoretical value. And also, the measured input resistance was larger than the calculated input resistance, and that's mainly because the voltage gain was lower than expected as well. Remember, in the equation we're dividing by a factor related to the gain, so when the gain is lower, Rin is a little bit higher. All right, we can see here with an input voltage of about 100 millivolts peak to peak, we get out about 1.98 volts peak to peak, so that was the gain of negative 19.4. And bringing the input voltage up to 200 millivolts peak to peak, we get an output of 3.28 volts peak to peak, but you can see we're starting to get distortion on the negative going portion of the output already. And that's one thing you have to be aware of with this circuit, is that it's got very limited output swing in the negative direction because of the low VDSQ value. Now, before we wrap up the video, there's a couple of things I'd like to elaborate on. One thing I should have mentioned from the outset is that the FET we're using here is the 2N7000. Those of you that watched the previous couple videos probably knew that, but someone coming in cold might be wondering what's going on. We are using a 2N7000 here. And as far as the input resistance goes, let's take a look at that just for a second here. We know that the input resistance is approximately equal to RF divided by 1 plus GM times R prime D. All right, GM times R prime D is the gain magnitude, and the actual measured value was 19.4 if we look at it as a positive number. So this equation for our actual circuit is 1 megohm divided by 19.4 plus 1, or 20.4. So our measured Rin based on this voltage gain is 1 million divided by 20.4, which gives us about 49,000 ohms. All right, and that's in much closer agreement with the measured value. That's what I would expect based on using the actual voltage gain. So that explains the discrepancy. And at this point, you're probably wondering, well, how did I measure the input resistance? Well, let me show you how I did that next, okay? And this is the circuit. I took the amplifier and I placed a 500K ohm variable resistor between the input source and the input of the amplifier, and that forms a voltage divider. What we've got here is our input source V in. Here's the potentiometer, I'll call it R sub pot, and here's the input resistance of our amplifier, R in. And what happens is, if R in equals R pot, then we have a voltage divider that splits V in evenly. We get V in over 2 here. So what I do is adjust the potentiometer until this value is 1/2 of the applied voltage. And then by definition, the resistance of the pot equals the input resistance of the amplifier. So we pull the pot out, measure the resistance between the wiper and this end, terminal C, and there we have the input resistance. And that wraps up today's video. I know this had some pretty tough parts in it. That algebra can really get a little confusing. And like I said, it's just something you need to practice. You get better at it as time goes on. But hopefully the next couple videos will be a little bit less dry and a little bit more fun. And I will see you next time around.